so I can see it. That's all that matters. Okay. Okay. So we are now recording even though you can't see it. So let me go to current slide. And as soon as the light comes on, I've got some good news for you, I think. I don't know if you count it as good news or not. I think I may have asked this question before, but maybe not. I teach so many classes, I can't remember who I asked what to. Are any of you WebAssign fans? No.
It's not bad to have for just
What's that?
It's not bad to have for just
Okay. And for that very reason, I have a WebAssign account for you. And I'll go on and put it on this slide. Well, I pressed the button. I'm pretty sure I did, but nothing happened. So let me try it again. Now something is happening. As soon as the lights come on, I can't figure out what's happening with my knee. This morning it felt great until at some point it just started, it's getting into the truck or the vehicle. It just hurt to cramp it up to get in. And then they said it was calling for weather. I'm wondering if I'm developing a weather forecasting knee because they said it might be calling for rain today. So I don't know. But here is your WebAssign class code. So if any of you went with the, what do they call it? Cengage Unlimited, and all you have is an ebook and you couldn't access it yet, here is your class code. Let me get my pen set up. It's Lawson, Lawson .al. I can't imagine what that stands for. 2435 space 1964. A very good year. I don't know what it was a good year for. But okay. That is your class code for WebAssign, for your ebook, for everything you need for the, whatever they call it, Cengage Unlimited. Okay? That's what you need. Okay? So, there's that. Now, I had hoped that by this time I would have everything set up on Blackboard, but it has been incredibly slow this time because I'm teaching from a new book in Math 100. I'm having to learn the ins and out of that, and its test bank was really awkward. You couldn't even get to it for a while, and then finally I did. And so everything is taking longer than what I thought it would. I'll get to it sometime. Okay, I only have 2 hours of office hours a day, and one of those is lunch, so I don't have a lot of time today. I only have 2 hours of office hours tomorrow, and one of those is lunch. On Friday, I have 4 hours of office hours, but I'm afraid we're going to be doing contracts or something else that's going to eat up my time. But I'll try. I'm trying in the evening to get things done too, but it's just really, really slow. And I've just run out of gas by the evening time. Since I'm low red blood cells and hemoglobin and hematocrits, I just don't have much energy at the end of the day. So I'll do what I can. All right. Any questions on anything we've done so far? Here's where we were. We're talking about, as Jordan said, definite integrals. Okay? Now, here is the thing that almost doesn't seem fair. The variable of integration in a definite integral is sometimes called a dummy variable. Now, it's not that we're making light of it or anything, but guess what? It can be replaced by any other variable without changing the value of the integral. Okay? Because guess what? The integral from 0 to 3 of x squared plus 2 dx is exactly the same as the integral from 0 to 3 of t plus 2 dt. It doesn't matter. You're going to integrate over the variable, plug in the numbers, and you're going to get a number either way. And you're going to get the same because the x plus 2 and the t plus 2, the dx and dt, they're equivalent to each other. They have the same value. So actually, it doesn't matter what you name that variable. You could call it Stickman, okay? You can name it anything you wanted to, okay? Fred, okay, that would work, okay? But because it all gets integrated out. Now, one reason they're telling us this is in a few minutes or sections or somewhere soon, we're going to do exactly that. We're going to change a little something just fairly minor and come up with a whole new expression that they use for a different purpose, okay? But it looks the same, okay? So, with that in mind, we move to the properties of definite integrals, okay? The definition of a definite integral of f on the interval a to b specifies that a has to be less than b. That's just how we do it. We always have a less than b when you're integrating from there to there. Because remember, this came from the sums, and you don't count backwards in the sums, you count forward, okay? So, ding, 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 ding. Perfect attendance again, folks. 2 weeks solid, 4 classes in a row, perfect attendance every day. Way to go. Keep it up. Okay, so back to this. We always, when you're doing your summation, you saw I equal 1 to n. Okay? Guess what? Those count forward. So start with the low number, end up with a higher number. So we just assume that the a is less than b. However, we can extend our definition to cover cases where a is equal to b. That's going to be very simple. Okay? Or a greater than b. And that's going to be pretty easy too. Okay? Now, geometrically, the next two definitions seem reasonably, or at least they tell us they do. Okay? For instance, it makes sense to define the area of a region if you had 0 width but finite height to be 0. Okay? If you have a rectangle, no width but 5 high, you still have no area. That's just a line. That has no area. Okay? Well, that is going to be when a is equal to b. Because you're going from 7 to 7. You're not going anywhere, okay? So that's going to be an area of 0. Okay? Because, well, all right, so here's the definition. If f is defined at x equal a, so it has to be defined there, otherwise you can't really do this, then the integral from a to a, in other words, you're not going anywhere if f of x dx is always 0. Okay? As long as x defined at a, there's not an infinite value there or something like that, that's 0. Okay? Which makes it sort of who would want to do that anyway. Okay, but that's what it is. Now, if f is integrable on a to b, but you put the b at the bottom and the a at the top, then that's just exactly the opposite. The integral from b to a of f of x dx is exactly the opposite of the integral from a to b of f of x dx. Because you're starting there and coming this way, so you have a negative width, you might say, and whatever your height was, okay? So that would make it a negative of what you have. So those are the two rules that take care of that. Most of the time, we like the b to be greater than a. Now, maybe not immediately, but we will run into some circumstances where we'll be doing that inadvertently. You know, it actually happens when we're changing the variable of integration, specifically when we're substituting or integration by parts. No, not by parts. Partial fraction. No, integration by parts, exactly. So there are some times when we'll do some substitutions, and that's going to reverse that just because of the way we substitute. Okay? And when that happens, we can just negate the, put it back, but put a minus sign in front. Okay? It's going to be pretty simple. Okay? Now, it says estimate, no, I'm sorry, it says evaluate the definite integral. Okay? I think I can do the first one. Can you? The integral from pi to pi of sine of x dx. Second?
Zero.
That's zero, because you're not going anywhere. You're going from pi to pi. Yeah, you haven't moved an inch, a millimeter, anything, so that's just zero. Okay? And then the next one. Okay? I think they want us to do this probably geometrically because they haven't shown us how to do a definite integral yet. So let's first rewrite that one. What would that be?
Integral of big to zero.
Is what?
Integral of big to zero.
Okay, yeah, so go change it from 3 to 0 to 0 to 3, but if you do that, what have you got to do? Put a minus out front, and then we'll do x plus 2 dx. Now, I think what they want you to do is graphically, okay? X plus 2, that has an intercept of 2, y-intercept of 2, and you're going x going to 3. You have a slope of 1, 4, 5, 6. Yeah. So, oops, not quite there. So anyway, you're integrating that. Okay? That would be 0 to 3 of x plus 2. Whatever that turns out being, and we know what that is, right? That's a trapezoid. Flip it over like this. So the little base is 3, the big base is 5. 3 plus 5 is 8. 8 times 3 is 24. Take half out of it, you got 12. Okay? Follow that? Doing the area under this curve. X plus 2 from 0 to 3 would be like this, right? Okay. That's the trapezoid. If you take this and flip it over there, move the 5 over here and 3 over there, you get a rectangle. Want me to do that in a different color? You pick a color. Say again? Red? Okay, let's try red. Okay. There's 1, 2, 3. 1, 2, 3, 4, 5. Okay. Okay. Now, can you imagine? Okay. So this is 5 and that's 3. No, 2. That's 2. And this width is the same, 3L throughout. This area is the same as that area, right? Okay. And this is a rectangle whose height is 2 plus 5. No, I didn't do it right, did I? 2. No, how did I get it? That's 7. 7 times 3 is 21, and half of that is 10 and a half, right? I don't know how I got the other thing. I was doing 3 plus 5 is 8, I think it was. Sorry about that. 2 plus 5 is 7. 7 times 3 is 21, and half of 21 is 10 and a half. So this will be, whoa, that's not what I wanted. That's what I wanted. Whoops, it didn't take. There we go. That would equal to minus 10 and a half, or minus 10.5, or minus 21 over 2. Okay? There's a lot of ways you can write your answer. Which, I'm sorry to do this. No, I'm not. Brings me back to WebAssign. By the way, did you see that when you came in about the code, the class code?
Did you send it?
Huh?
I didn't see it.
Okay, right. Okay, let's go back. Hold off on what we're doing here. Right there. There's our class code for your ebook, WebAssign, everything that you need. It's Lawson, LAWSON.AL space 2435 space 1964.
Yeah, it has to be a space in between.
What's that? I think so.
Okay.
I think so. Okay. That's how they sent it to me. So I haven't tried it, so I'm not even sure I can get into it. I should be able to, but that's how you do. Okay, right. Now, I wish I had left it up here. After the last class, a student came to me and said, she wrote the problem on the board. I saw it on her phone, and the answer was x squared plus x minus 1. And any way you did it, that was going to be your answer. And Webatown told her it was wrong. And I don't know what they were looking for. On this one, like I just said, now, this is why I said this. Minus 10 and a half would be a correct answer. Minus 10.5 would be a correct answer. Minus 21 halves would be a correct answer. But guess what? Webatown only going to recognize one of those. So most of the time you go look at it, oh yeah, well that's the same answer. Yeah. But sometimes they just tell you, wrong answer, try again.
It did be like that last semester.
Huh?
I said it was like that last semester on certain problems. It wasn't all the time, but you
Yeah.
would come across one that was like that.
Yeah. And you think you did something wrong in the problem, when really they were just looking for a different way to write the answer. And that's the thing that gripes me about WebAssign. And hers, there's no other way you could have written that answer. Hers was absolutely correct. There's no other way you could have written it. And they still told her it was wrong. So guess what? Computers are programmed by people, and people make mistakes. Okay? So don't get frustrated with it. I do. Don't you. Use it as a tool, but don't let it rule you. Okay? This book, he has LarsonCalculus.com as a free website. He has CalcChat.com as a free website. He has CalcView.com as a free website. Use them, okay? But if you want to use WebAssign too, you can. You certainly can. Okay, so that's what I suggest the answers are. Let's see what they say they are. Okay, the first one, 0. Absolutely right. Going from pi to pi, you're not going anywhere. You haven't traveled anywhere. 0. Okay. Now, this one, 3 to 0 of that is the same as that given in example 3b. Okay. Okay, we had already done 3b, except that the upper and lower limits are interchanged, so you have the same answer as we did before. That would be minus that one, so that would be minus 21 halves. So that's the answer they were looking for. Minus 10 and a half, minus 10.5, all those would have been correct answers. Okay? Make sense? Go back and see 3b. We did 3b in class last time, and we got the right answer. And it's just the opposite of it because you reverse the thing. Anytime you have large, small, flip them, put a minus sign. Okay. Next, that was example 4. Okay. Oh, and by the way, I was saying this, example 4, see LarsonCalculus.com for an interactive version of that type of an example. So if what I've said isn't making crystal clear sense to you, go to his free website and you can see it there. And maybe he'll present it in a way slightly clearer for you than what I'm doing, and then use that. All right, so next. In this figure, the larger region can be divided at the point x equals c. Okay? Fine. Okay? And can be divided there into two subintervals. Now, there's nothing magical about C. They're just saying you can do it. Okay? Frankly, if it had been me, I think I would have moved it over here and made that the C, because that looks like the minimum value. Not that there's anything special about that, but you could do it that way. Okay? But any C in there. And because it can be divided, and you're talking about the same area, And it's the same function here, f. You could say, instead of the integral from a to b of f of x dx, which would be this area here, you could say the integral from a to c of f of x dx, which would be this one, plus the integral from c to b of f of x dx. And that would be this one. These two added together give you the original. So you can partition any continuous function, in fact, any function, into partitions and do it that way. Because the line segment has zero area, you're not losing anything there. It follows that the area of the larger region is equal to the sum of the areas of the two smaller regions. When I first looked at that, I said, which one's larger? You know, they meant the whole area as opposed to the two smaller regions. Okay? So this leads to theorem 4.6, additive interval property. If f is integrable on the three closest intervals, three closed intervals, three closed intervals determined by a, b, and c, as in that picture, the integral from a to b of f of x dx is exactly the same as the integral from a to c of f of x dx plus the integral from c to b of f of x dx, as in that picture. Now, I'll tell you why I would have chosen this point down here, okay, the minimum point. Because what if I had wanted to reverse this and make it dy's rather than dx's, okay? Then by taking the integral here, that would all be certain values, and then the integral here would be other. When you do this, you run into real difficulties because they don't work as well. It is not, it fails the vertical line test. Hey. Okay, no problem. Okay. So, just another tool, put in your tool belt. When you need it, use it. Okay? Here's one example where you would need it. What is the integral from -1 to 1 of absolute value of x dx? Well, guess what? Absolute value of x is not a smooth function, okay? Because if you think about the absolute value of x, you remember how that graphs? It graphs like this, okay? At -1, it has a value of 1. And at +1, it has a value of 1, okay? But it's not particularly smooth, okay? Because this is a piecewise defined function. So since it's a piecewise defined function, do the pieces as you do. Integrate that one, integrate this one, and add them together, okay? So you're going from -1 to 0 and from 0 to 1. But remember, the absolute value of x is defined to be minus x for all x is less than 0 and x for all x is greater than or equal to 0. Okay? So therefore, that's how we define the absolute value, because when you have negative x's, it's the positive value, minus x. When you have positive values, it's just x. Okay? So since that's the case, do one integral from -1 to 0, that's where it's less than 0, and there you put your minus x in, and then the other value is just x, because it's positive over here, so it's integral from 1 to 0. Okay? Now, we can do this one geometrically, 1/2 the base times the height. Well, 1 by 1 is 1, half of that is 1/2, half of that is 1/2. That area is 1/2. Add them together, you get 1. Does that make sense? Because this, if you completed this, that would be a square, right? 1 by 1. So that would be an area of 1, and half of that would be an area of 1/2. This would make a square, 1 by 1. Area of that would be 1, half of that would be 1/2. 1/2 Make sense? I'm going to be so glad when we quit having to do it geometrically. Not going to be that much longer. Let's clear what we got here. Okay. Oh, so nice. They just write down the answer. 1/2 plus 1/2 is 1. Okay. They didn't tell you how you did that, but I showed you how they did it. Okay. You thought mine was too short. Okay. Look at what they did. Okay. All right. So here is theorem 4.7, property of definite intervals. Okay. Properties. If f and g are both integrable functions on some interval from a to b. It's easy to cross up the words pretty easily. Integrable or integral on an interval. Okay, so yeah, interval of a to b, integrable functions on that interval of a to b. K is any old constant. Then the functions kf and plus or minus, or f plus or minus g are also integrable on the interval a to b. And the first one, the integral from a to b of k f of x dx, remember k is integrable, so you can do it. Pull that constant out front, just like we did in indefinite integrals. Pull it out front and then do the integral of a to b of f of x dx. Or if you have f plus or minus g, both of them are integrable on that interval, okay, then this would be the integral of f of x dx from a to b, plus or minus the integral, which we know we could do, of g of x dx. So, basically just like we did with indefinite intervals. Okay. Notice property 2 of theorem 4.7 can be extended to cover any finite number of functions. You can have f, g, h, I, j, k, p, l, q, m, and p, o. Go on and on forever, and then add and subtract them, then just split them up and do each one separately with the proper sign in between. Okay? Make sense? All right. Hopefully this is fairly good. Okay. So let's do this one. Let's let us go on and evaluate it. But they're saying, if the integral from 1 to 3 of x squared happens to be 26 over 3. They don't tell you why, it just is. Okay? And the integral from 1 to 3 of x dx is 4. And the integral from 1 to 3 of dx is 2. They just tell you that. They don't tell you anything else about it. It's just that. I will tell you they are correct, okay? But they haven't told you why they're correct. But if that's the case, then what in the world would be the integral up here? What would that be? It'd be a negative, the integral of 1 to 3 of x squared dx plus pull the 4 on the outside, integral of x dx from 1 to 3. This is splitting them up like we did before, minus 3 times the integral from 1 to 3 of dx. Right? What the rules before said, if you have a coefficient out in front, pull it out. And then you're left with just integral from 1 to 3 of x squared. Then put the plus here, and pull the 4 out, the integral from x dx from 1 to 3 of that. Pull out the minus and the 3, and do the integral of just dx. You pulled out the 3, and all you have is dx. But guess what? They just told us what this one is. They told us what this one is, and they told us what this one is. So now just plug in. Okay? That would be a minus, and what's the integral of this? 26 over 3 plus 4 times, and what's the integral of that? 4. minus 3 times the integral of that, which is 2. Okay, so this will be minus 26 thirds plus 16 minus 6, which is 10 minus 8 and 2/3. Is that right? Or maybe easier, make this 30 thirds minus 26 thirds. And that would be 4/3, which is 1 1/3. Exactly. Okay? Really bizarre the way they set this up and done it. It's absolutely right. They're just saying, if you already knew that, and they didn't tell you how you knew it, but if that was true, and I'll tell you it is true, then this is what you would do. Okay. Please, folks, tell us how to evaluate these things. You're holding us in suspense. Okay? And that was example 6. Yeah, we had done example 5. Okay. One more little theorem, I think. Well, let's clear this out of the way and see how they did it, which I think is going to be exactly like we did, hopefully. So, they rewrite the problem, and then they break it into little pieces. Okay, so they're taking an extra step. The integral from 1 to 3 of minus x squared dx, plus the integral from 1 to 3 of 4x dx, plus the integral from 1 to 3 of minus 3 dx. They put the minus in there. Fine, they could have put the minus on the outside. Okay? Now, what they're going to do to the first integral is bring out the minus 1. What they're going to do to the second one, bring out the 4. What they're going to do to the third one is bring out the minus 3. As long as those are constants, you can do that. Okay? So that's what they did, bring out the minus 1. They don't write the 1. Bring out the 4 and bring out the minus 3. We went there in one step, they took 2 or 3. Okay? And then you just plug in what those values are from above. That's minus 26 thirds plus 4 times 4 minus 3 times 2, which is 4/3. They skip steps like crazy down here, and there's all sorts of steps up there. Fine. Any questions on that? Okay, one more little slide before we finish here. If f and g are both continuous functions on some closed interval a to b, and 0 is always less than f of x, and f of x less than or equal to, and f of x is always less than g of x on that interval from a to b. In other words, here's 0 down here, here's f, and here's g. F is always greater than 0, and g is always greater than or equal to f. Okay? Then the following properties are true. First, the area of the region bounded by the graph of f in the x-axis must be non-negative. Because if f is greater than 0, everywhere on the interval, it's got to be a positive area. If it was below, then some of that would be negative. But if it's all positive from a to b, it's got to be non-negative. Okay? It could be 0 if f was exactly 0. Second, the area must be less than or equal to the area of the region bounded by g in the x-axis, because g is always greater than or equal to f. Okay? So the areas have to be similar. The integral for f of x dx will always be less than or equal to the integral of g of x dx if f of x is always less than or equal to g of x, and they're both always positive. Okay. So those two properties are generalized. What two properties? Okay. The preservation of inequality. If f is integrable and non-negative on the closed interval a to b, then it's got to be positive. That's the first one. Okay. It's got to be greater than 0. Okay, not positive. Non-negative. Okay. and if f and g are integrable on the closed interval a to b, and f is always less than or equal to g on for every x in that interval a to b, then the integral of f of x dx has to be less than or equal to the integral from a to b of g of x. So in other words, if this is true, you can put the integration signs in it, dx's, and that's got to be true on the closed interval a to b where that's always true. Okay. Doesn't seem like it's earth-shattering, but it's there. All right. That ends the section. Homework exercises, do number 3. Answers in the back of the book. Worked out solutions at calcchat.com. It also has more detail at calcview.com. Do any of the odds 5 through 7? They're all at CalcChat. 7's at CalcView. Do number 11. It's at CalcChat, not at CalcView. Do any of the odds 13 through 21. They're all at CalcChat. None of them are at CalcView. Do any of the odds 23 to 31. They're all at CalcChat. 25's at CalcView. Do any of the odds 33 to 39. They're all at CalcChat. 37's at CalcView. Do either 41 or 43 or both. They're both at CalcChat. Do 45, it's a CalcChat. And there's a think about it at 47, and you can think about it and do it whether you want to or not. Okay, that should be at CalcChat. There's another one at 49. You can do either one of those or both if you choose. And there's another one at 51. So do any of the three, one of them, two of them, or all three. And then there's exploring concepts. You can do 53 if you'd like. It should be at CalcChat. And then there's a verifying a rule at 55. You can do that if you choose. You don't have to. And then 57 is one that says using different methods. That's that function we've seen before. So take a look at it and see if you want to do that. Then do either 59 or 61 or both. They're both at CalcChat. They should be. There's a true-false at 60, odd 63 to 67. You should be able to find those answers at CalcChat. There's a Riemann sum problem at 69. You could do that at CalcChat. And if you're into proofs, you can try doing 71. By the way, are any of you math majors? All of you pre-engineering? Okay. This may be a gross generalization, but I find that most of the time the engineers don't really interested as much in the proofs as the math majors are. So that's why I asked. So if you're not into proofs and you don't want to do it, I think you can live without it. But they're sort of fun to do too. Okay, 73 is another think about it. You can think about doing it if you want to or not. 75 is finding values, and these should all be at CalcChat. And then there's another think about it at 77. You can think about that one. And then using a Riemann sum, you can think about that one as well. Okay. Hallelujah, we're finally at 4.4, which is fundamental theorem of calculus. Okay? And from this point on, you never have to go back and do those Riemann sums again. No, I shouldn't say that. They were fun while they lasted, weren't they? Yes. Okay. Wait a minute. We were just there. I was talking and not paying attention. 4.4, that's where we're heading next. Okay, sorry, we have to wait for PowerPoint. At least it's not the new Math 100 course. That book has split every PowerPoint presentation averages about 5 slides. So you're always closing, opening, closing, opening, closing, opening. This one, at least you get more than 5. Okay. I thought it was going to open, but oh, maybe it did open. Nope, not yet. some reason it's not opening. So what I'm going to do is close this and try it again. 4.4. Sometimes PowerPoint works and sometimes it just sits there and does stupid things. There, it opened. Okay. And we'll go from current slide. And all right. 4.4, fundamental theorem of calculus. Okay. Our objectives here, we'll evaluate a definite integral using the fundamental theorem of calculus, so much easier than the other ways. We'll understand and use the mean value theorem for integrals. We'll find the average value of a function over a closed interval. We'll understand and use the second fundamental theorem of calculus. Now, in some books, they call this fundamental theorem of calculus part 1 and part 2. This one calls it fundamental and second fundamental. Okay? My brother Darryl, my other brother Darryl, I don't know. And we'll understand and use the net change theorem. Okay. So first, let's start with the fundamental theorem of calculus. You have now been introduced to two major branches of calculus. Differential calculus, that's pretty much Cal 1. Integral calculus, you sort of were getting your feet wet at the end of Cal 1. What we've been doing so far is pursuing that, getting our whole body submerged. Okay. At that point, we'll use two problems. The two problems seem unrelated. They are not. Very close connection, and we'll get there. The connection was discovered independently by both Isaac Newton and Gottfried Leibniz, and is stated as the fundamental theorem of calculus. Now, these two guys disputed with each other that they both did them independently. Newton was convinced that Leibniz had copied his work and published it first. And because Newton was he was so particular, he didn't want to publish anything until he was absolutely certain it was totally correct. And because this was brand new stuff, he wasn't absolutely certain. So he sat on it and stewed on it and worked with it and stuff for years. Gottfried Leibniz saw it and published it. Okay. Now, whether he saw it from Newton or did it on his own, that's the proverbial debate. We'll never know, I guess. Okay. So, informally, the theorem states that the differentiation and definite integration are actually inverse operations of each other. Think about it. Hasn't that been true of math all along? Way back in elementary school, what was the first operation you learned? Addition. And you did all those flashcards and tables and memorization and that kind of stuff. When you finally thought, ooh, finally we're through with that, then they turned around and had you undo it and subtract it. And subtraction undid addition. You thought, okay, we got math down now. Nope. They came up with multiplication. And once you did flashcards again and all those things, then when you thought you finally had it, then you undid it with division. Later, much later, you did raising things to powers. And then sometime after that, you took roots. That undid powers, right? Well, all along you've been doing things that undid other things. Well, guess what? In calculus, the same way. Differentiation does one thing, integration undoes it. Integration does one thing, differentiation undoes that. They're inverse operations. Same sense that division and multiplication are. To see how Newton and Leibniz might have anticipated that, let's consider the approximation shown below. I'm not absolutely convinced this is going to be all that illustrative, but let's give it a shot. Okay. Before calculus, what we did was estimate average rate of change using the secant line. Change of y or change of x, that gave you slope. Okay? But you just pick a point here, pick a point there. It wasn't exactly the path you traveled, but it's the average. Okay? The tangent line, on the other hand, gave you the instantaneous rate of change at that point right there. This is the average between these 2 points. So what's the difference here? Okay? The average, the area of the rectangle dy times dx. dy times dx. That's this dotted rectangle. That area is there. Now, fine. And this is the area under the curve. And that's they're not the same. Okay? They're definitely not the same. Oh, okay. I think I see what they're saying. So okay, back it up here. Well, it's still, there's something bizarre here. I think what they mean here, this should be dy dx. This is delta y over delta x. This is dy dx. This is delta y times delta x. This would be f of x dx. Okay. If they had done it that way, I would be a lot more comfortable with it. I just don't. As I said to begin with, I'm not sure this is going to be all that illustrative. Because to me, those two things don't make a lot of sense. I know what they're trying to say, I know what they're heading for, but I don't like the way they're saying it. Okay? But let's get to the slope of the tangent line was defined using the quotient delta y over delta x as long as the delta x is going to 0. That's the slope of the secant lines as delta x goes to 0. Similarly, the area under a region of a curve was defined as the product delta y delta x, the area of a rectangle. So at least the primitive approximation stage, the operations differentiation and definite integration, appears to have the inverse relationship in the same sense that division and multiplication are inverse operations. Okay. So the first part of that, this part and this part, they kind of make sense. Okay? Yeah. One's a division, one's a multiplication. Okay. You can sort of see how they could be kind of inverse. Okay. The second part, not quite as clear. Okay. Okay. So at least in the primitive, okay. The fundamental theorem of calculus states that the limit processes used to define the derivative and the definite integral preserve that inverse relationship. I guess that's what they're saying, though the pictures didn't help any, but that's what they're saying. So here's the fundamental theorem of calculus. Finally, the fundamental theorem of calculus. If a function f is continuous on some closed interval a to b, and capital F is the antiderivative of little f. Remember we did this? It now seems like so long ago, you may have forgotten it, but we did do it. You know, when we did indefinite integrals, we just did antiderivative on that interval from a to b. But with an antiderivative, we just said, if you didn't have these, you just said f of x plus c, right? Capital F of x plus c.
C's with a constant.
Yeah. Okay, where capital F was the antiderivative of little f. Okay? We just said f of x plus c. Capital F of x plus c. Now what we do is do the capital F of x just like we did before, but evaluate it at the upper thing and subtract from that the evaluation at the lower thing, and we get the area of that. Okay? Now, that's fundamental theorem of calculus. This is how you do definite integrals. Okay? And sure, this makes it so much easier than all that geometric stuff we did, all the summations we did, and remembering those formulas. If it's an x squared, that's a x or n, n plus, all those things. Don't have to do those anymore. So the following guidelines can help you understand the use of the fundamental theorem of calculus. They say. provided you can find the antiderivative of little f. If it is a function you can find the derivative, the antiderivative of, you now have a way to evaluate definite integrals without having to use a limit, without having to use geometry. You just do it, which is what I've been waiting for. When applying the fundamental theorem of calculus, the notation shown below is convenient. The integral from a to b of f of x dx is, if the antiderivative of little f is capital F, then write that down just like we did for indefinite integrals, remember? But rather than doing a plus c, we then put the bracket here going from a to b. What does that mean? Plug in the b for the x here, do f of b minus f of a. That's what you do. For instance, okay? The integral from 1 to 3 of x cubed dx. What's the antiderivative of x cubed?
3x squared.
Not quite. X to the fourth over 4, is that what you said? I think it was, wasn't it? Yeah, that was pretty close to what you said. Okay, x to the fourth over 4. Now, rather than putting a plus c after it, we put the limits from 1 to 3. 1 at the bottom, 3 at the top. And then you take and plug in there, what's 3 to the fourth power? 81 divided by 4. 3 to the fourth divided by 4. Minus, and what's 1 to the fourth power? 1. Okay, good. So minus 1 over 4. That's 81 over 4 minus 1 over 4. That would be 80 over 4, and 80 over 4 is 20. Is that easier than some sort of a getting it into the ends and the Riemann sums, or trying to do it geometrically, which this one I don't even know how you would do that geometrically. That's how you do it. Notice there's no longer an x in your answer. It's just a number. Okay? Definite integrals produce numbers. Indefinite integrals, the x is still in there. Plus c's. Okay? You always had to have the plus c. But with definite integral, you wind up with numbers. It is not necessary to include a constant of integration c because you're taking care of it. So this would be f of x. If you put the plus c in there like we did before, evaluate that from b to a to b, okay? Then you have f of b plus c minus f of a plus c. This is a plus c here and a minus c there, still f of b minus f of a. So you don't need the plus c's anymore. They're going to subtract out anyway. So it's just f of b minus f of a. Whatever the antiderivative is, evaluate it at the top minus the antiderivative evaluated at the bottom. Thank you for giving us fundamental theorem of calculus.
Just 1 second.
Second?
Just 1
Yeah, I will. I'm just going to sit and rest a while. Okay. Oh, this is so much nicer than all that other mess we were doing. What's that? Yeah, we're just doing the antiderivative just like we did in indefinite integrals, except.
Can you do it real quick?
What's that?
Work it out?
What, this one?
Yeah, the x to the third. Just
Okay.
on the board.
Okay, remember that what the okay. Let's go back and think about what the rule was for taking a derivative. Let's take let me get my pen back. Okay, so let's say you had x to the nth power. And if you're taking a derivative of that, we do n times x to the n minus 1, right? That's taking a derivative, right? Right? Okay, so what you did, you took the exponent, multiplied the exponent times the variable, reducing the exponent by 1. So an antiderivative, if you're integrating x to the n dx, then what you do, you take the x to the n plus 1, you add 1 to it, not subtract 1 from it, but rather than multiplying by the n plus 1, we divide by n plus 1. You see, you do two inverse operations. Rather than subtracting, you add, and rather than multiplying, you divide. You divide by that same thing. So since this was x cubed, you do x to the fourth, but then divide by 4. And how did I say you could check this? Always take the derivative of this. Derivative of x to the fourth is 4x cubed. So 4 over 4 is 1, so you wind up with x cubed. So we were already doing that going the other way. Now we're doing it going this way. Okay? So is that what you needed? Okay. A little bit of refresher because it's been a while. Okay? Got it? Done now, everybody? Any more? Okay. So let's evaluate some integrals. Oh boy, fun time in the old time tonight. Okay? Now you want to do several steps here? We can. Get used to it. This is integral from 1 to 2 of x squared dx minus 3 times the integral from 1 to 2 of x, of dx, I'm sorry, dx. Okay? Is that okay? What I did was just put this in the 2, and just the integral of x squared dx is the first one, and then pulled out the minus 3 and just did the integral of dx. Right? Now, what's the antiderivative of x squared of x squared? Say again? Not quite. X cubed over 3. Not 2x cubed over 3, x cubed over 3. Don't combine the two. Don't multiply and divide. Just divide. Okay? Evaluate that from 1 to 2. Minus 3. And what's the antiderivative of dx? X, okay? 3 times x evaluated from 1 to 2. Perfect, okay? So do that one. 2 cubed is 8 thirds minus 1 cubed is, so that'd be 1 third. Now we have a minus 3 here, and let's do this one. What would that be? X evaluated at 2 would be pretty easy. 2 minus 1. Got it. Okay? So what would this be? This would be 7 thirds minus 3 times 1. So that would be 7 thirds minus 3, which would be 7 thirds minus 21 thirds, right? That's what 3 is, right? No. No. 9 thirds. I was doing sevenths, okay? Don't agree with me, okay? Minus 9 thirds. The head's not working well today, okay? And that would be minus 2 thirds. Okay. Now, and guess what? We don't care that it comes up a negative number. When we were doing areas, we didn't like negative numbers. So we had to do all sorts of weeping and gnashing of teeth because we're trying to figure out why that's the case. Well, we sort of know why it's the case now. This is a parabola that dips down below the x-axis. So it's not at all surprising that you might have a negative area because almost below the x-axis. You do, fine. It all comes out in the soup or in the wash somewhere. Okay? All right. So we got that as an answer. We'll check it later. Okay? Now, the time comes, the walrus said, to think of many things. Okay? If we are going to do this one of the first things I'm going to do is pull the 3 outside and make that the integral from 1 to 4. But before I write the square root of x, what do you think I might suggest that you write that as?
Fraction.
Yes, use a fractional exponent. And what would that be? X to the 1/2 power dx. Okay? Now we can go back and use our power rule. Don't forget the 3. It's out there. 3. And what is the antiderivative of x to the 1/2? What was the rule? Add 1, and 1/2 plus 1, which is to be 2/2, would be 3/2. And then you put it over 3/2, but since that's a fraction, I'll write that as times 2/3. Is that legal in most states? Okay. Dividing by 3/2, which is what we do, divide by the exponent. Dividing by 3/2 is the same as multiplying by 2/3. Invert and multiply.
Okay. For some reason I was thinking it was a plus 1 too when you.
Okay, yeah, you add 1 to this, and 1 is 2/2. 2/2 plus 1/2 is 3/2. So that gives you your exponent. And then you take the exponent and divide by that, but since you're dividing by a fraction, that's multiplying by its reciprocal.
Right.
Okay.
For some reason I thought you did something in the previous slide like it was plus 1 but now.
You did, and you, well, yeah, whatever was up here, that goes into the denominator. 3/2 goes in the denominator.
So it's already assumed.
And dividing by 3/2 is the same as multiplying by 2/3. I'll just do it 2 steps at once because I'm lazy. What's that? Okay. Here you're multiplying by 2. Is that what you meant?
No, he's saying 3.
Oh, by 3 on the outside? Yeah, you're going to do that, and that was my next step. Okay? You're getting it. You're getting it, except I want to put from 1 to 4. But before I evaluate it, I agree with you. Let's divide out the 3s. Okay? I love it. That makes it much easier. And in fact, I would even say factor out the 2 and then just do the evaluation here. What is 4? So I'll write it out. 4 to the 3/2 power minus 1 to the 3/2 power. Right? Now, so that's 2 times. Now, when I'm doing a fractional exponent, usually it's easier to take the square root first. What's the square root of 4? 2. Cube 2 and you get 8. Okay, so that would be an 8 here. Okay, minus, and then what's the square root of 1? 1, and 1 cubed is 1. So that would be 8 minus 1. So this would be 2 times 7 is 14. Okay? Isn't it though? Oh, can you imagine doing that as a Riemann sum? Oh, please don't, shoot me and put me out of my misery.
I looked at it like before you went over, I was like,
Yeah. This is so much nicer. So much nicer.
We ain't gonna have none like the other ones geometrically way on the test.
Okay, you know what I'm going to do on the test? I'm going to say evaluate the integral. And if you want to go back and do it, knock yourself out, okay?
nah, trust me, I'm good.
Okay.
I'm good, bro.
All right. I don't think I like them any more than you do. Okay, so I'm not a pure mathematician, I'm a physicist, okay? All right, can I erase those?
Yes, sir.
All right. Now remember what the answers were because I've already forgotten what the first one was. Okay, how about this last one? What is the antiderivative of secant squared? Oh boy, how'd he get that? I think he just made something up. Okay, think of your derivatives. Derivative of sine is cosine. Derivative of cosine is minus sine. Derivative of okay. Well, when in doubt, see if you can find the table somewhere. Okay. Oh, here's one at the front of the book. Derivatives and integrals. Oh, you don't have books. I'll forget that. Okay.
Mine's missing.
I'm gonna have mine like next week.
Okay.
Like, I'm getting everything for sure.
But if you go to the front of the book and you see derivative of the tangent is secant squared. So guess what the antiderivative of secant squared is? Tangent x. And we'll evaluate that from 0 to pi fourths. And what is that? That's the tangent of pi fourths minus the tangent of 0. Okay? Now, anyone remember what the tangent of pi fourths is? I'll have to talk with your trig teachers. Okay. Okay, you're thinking of the right, that's what the sine or cosine of pi fourths is square root of 2 over 2. So since tangent is sine over cosine, that would be root 2 over 2 over root 2 over 2, which is 1. All right, so this would be 1. And does anyone remember what the tangent of 0 is? It's 0, because it's sine of 0 over cosine of 0. Cosine of 0 is 1, so 0 over 1 is 0. So guess what? 1 minus 0 is 1. That's it. 1. Yes?
What is the purpose of knowing sine, cosine, tangent?
Okay.
What can it be used for, though, is what I'm getting at.
Okay.
We have to remember.
All right. Let's say you're a forester, okay? And you want to estimate the board feet of lumber in that tree there so you can make a reasonable bid and not lose your shirt, okay? So one way to estimate the height of that, you could tie the end of your measuring tape to the bottom of the tree and climb the tree running out your tape and figure out how tall the tree is. Or you could use a sextant and get the angle and take the tangent of that over this, the distance you are from the tree. Now I'll let you decide which one you want to do.
You gotta have some pretty long tape.
Yeah, and a lot of skinned arms and broken limb. No, yeah, either the tree limbs or your limbs. I don't care which one. Something's gonna break there, I bet. You know. So yeah, much easier to use trig. Okay, in many applications. When you're building trusses, you know, to get your angles and the measurements. What's that? I can't hear you. A couple more of those? Okay, let's first see how they did these. So let me erase this and see if they did it. Yeah, I hope you all wrote it down so you can remember. The first one, and they didn't split it into 2, they just did it as it was. The antiderivative of x squared is x cubed over 3 minus 3 times x. They just did it like that. And that's fine. That's how I would have done it too. I was dragging it out so you could see all the things we've done before. And then evaluate that from 1 to 2. So plug in the 2 first, and you have 2 cubed over 3, which is 8 thirds minus 6. Then minus a 1/3 and minus a minus 3. Okay? Let's see if they did that. 8 thirds minus 6 minus a 1/3 minus 3. And they just write down the answer, okay? They didn't show you how they got it, but negative 2/3 was what we got to, remember? What's that?
You always subtract.
Yeah, you always do the antiderivative with this number plugged in minus the antiderivative with this number plugged in. Yeah, you always, that is always a subtraction here.
Okay.
These subtractions came with the problem,
Yeah.
but that always is the case. Okay, and that was what we got before too, negative 2/3. I remember that one. Okay, the next one, just like we did, they pulled the 3 on the outside and rewrote the square root of x as x to the 1/2 power. That then is something I can do an antiderivative of, and that would be 3 times x to the 3 halves, and they divided by the 3 halves. I just went on and multiplied by 2/3. To me, that was so much easier. Yeah. Evaluate it from 1 to 4, so that would be, and they just skip steps like crazy, don't they? Okay. Where did that come from? When you invert and multiply, and that becomes 2/3, the 3's cancel out, and you have 2 times 4 to the 3 halves minus 2 times 1 to the 3 halves. So it's got the same thing we did. They just skip steps like crazy, and you have to think through and do what we did to get there.
So the ones we did geometrically, we could have did it this way.
Say that one more time.
The ones we did before this.
Yeah. Well, we did it almost this way, except I said 2/3 rather than, or 2/3 times 2/3 rather than divided by 3 halves.
I'm talking about like way before this.
Oh yeah, yeah, yeah. When we're doing Riemann sums and all that, yeah, do them this way. Absolutely. Don't try doing them geometrically. Do them this way. Okay, so much easier. And this will be. They come up with an answer of 14. I believe that's what we had, wasn't it? I sure hope so. Huh? Okay, and then the C one, the antiderivative of secant squared is tangent. Evaluate from 0 to pi-4. Now here's one you have to be very careful on. And most of the time they won't give you something stupid, but if this had been 0 to 3/4 pi, you could not. Anyone tell me why? Picture what the tangent function looks like. Okay? The tangent function starts at -infinity, goes up, goes through 0, passes through 1 at pi-4, and goes to positive infinity. Where? At pi halves. And if you tried to integrate over to the 3/4 pi, you have a discontinuity in there. Yeah. Yes. Could not do it because it's going to infinity in between. But between 0 and pi-4, it's all good. And that comes up being 1.
So we would have a question where the answer would be does not exist?
Yeah. You think I would give you one like that? Ah! Okay. All right. So there's example 1. I haven't been paying attention to where we are in the book. Okay, here we are, example 1. So let's move to, do we have time? I think we have plenty of time. Yeah, okay. All right. Oh, they skip example 2. They skip example 3. Shame on them. Oops. Let's do example 2. And you wanted a couple more? You got them, Toyota. Just ask, okay? Now, let's evaluate 0 to 2 of absolute value 2x minus 1 dx. It's probably not what you had in mind, was it? Okay. Now, this absolute values are piecewise defined function. I didn't write it. No, I did write it right. Oh, yeah. Okay, sorry. Okay. What you almost have to do is what they did, graph it. Okay? Pain in the neck, but graph it. Okay? So let's do, actually you're in the first quadrant, so you don't really need that, but we just won't go there. So here's 0, here's 1, and here's 2. Okay? Now, what we're going to do is, or what I'm going to do is graph first. Give me a different color. Blue. Light or dark? Light? Okay. What I'm going to do is graph this. Y is equal to 2x minus 1. I'm going to graph it from x equals 0 to x equal 2. Okay? I'm going to do that first. Okay? Now, where would I begin? Y-intercept of minus 1. So let's go down here. Oh, I didn't put the 1, 2, negative 1, negative 2. Y-intercept of minus 1. Slope of 2, right? So that means for every 1 you go over, you go up 2. For every 1 you go over, you go up 2. Okay? So this would be, the blue line here would be that function. But we're doing the absolute value of that. So anywhere where this is positive, that's going to be it. But anywhere where it's negative, you have to flip that. Okay? So that means we're actually coming from plus 1 down to 1/2. This value here is 1/2, by the way. Okay? So the absolute value, I probably should have gone back to my dark blue then. Dark blue. Okay? And this would be the absolute value function. Here to there. So you see that? Because the absolute value can't be negative, so you have to flip this over and make it positive. So this then makes it a piecewise defined function. That would be the integral from 0, oh, and by the way, here's how you would write that. The absolute value of 2x minus 1 would be minus of 2x minus 1 anytime x is less than 1/2, and it's positive 2x minus 1 anytime x is greater than or equal to 1/2. That's your piecewise defined function. Right? Because you have to negate this over here, because you can't have a negative value, so you negate it. You flip it over and make it the opposite value. Okay? Because you see, let's take x equals 0, for instance. That would be less than 1/2. X equals 0, that would be a minus 1. We want it to be a plus 1. So we have to have minus 1. Okay. So now we do our integral. Integral from 0 to 1/2, because that's what you're integrating here. Okay? And rather than writing it this way, I'll write it as 1 minus 2x dx plus the integral from 1/2 to 2 of 2x minus 1 dx. I'm getting all over the place. Can I erase some stuff to make it less crowded now? Is that okay? Okay, so let me erase this, okay? And this, okay? And that's okay. Whoa! Yeah, I guess we're okay. And frankly, I think you'll find this is true. Sometimes when you're integrating, you're doing this kind of stuff, you'll find setting up the problem is the hard part. Doing the integration is the easy part. Okay. This is what we've got now, based on what we drew before and the other things. So let's do this one. What would that be? It's the antiderivative of 1, or dx. Help me, somebody. Antiderivative of 1 dx. Oh, yeah, okay. I thought you said dx. Okay. X minus antiderivative of 2x is what? Huh? You're taking the derivative, antiderivative. X what? X squared. Right? That's it, exactly. And we'll evaluate that from 0 to 1/2. okay, plus, now do the antiderivative of 2x. X squared, okay, minus antiderivative of 1, no, x, okay. Evaluate that from 1/2 to 2. See what we did? Okay, you had me erase it. You did the one like this from 0 to 1/2. That was the reverse of this one. Okay, the opposite of that one. So I wrote it as, maybe should have put it in parentheses here. What's that? I can't hear.
You going on base where it hit the x-axis.
Yeah, you're going along the x-axis from 0 to 2. For the first 0 to 1/2, you're in this one, and then from 1/2 to 2, you're on that one. Remember, that's where the v was. The v was at 1/2. So you did the positive part here, and then the positive part there, because this is the absolute value. And so that was the opposite of this for the first part of that, 0 to 1/2, and then positive, that part from 1/2 to 2. And it just reversed the order of those. So let's plug and chug here, folks. Evaluate at 1/2, what would that be? Plug it in, plug it in. 1/2 minus 1/4. And I'll do the 0 part. 0, okay. I saved you some work there, okay. Plus, plug in the 2 part, and what do you get? Say again? 4 minus 2. Okay, I'll put that in parentheses. Minus 1/4. There's more. Minus 1/2, right? Got it? Okay. That's, okay. Okay, no, I got it. Okay. So, this gives you 1/4. 1/2 minus 1/4 is 1/4, right? Plus, this will be a 2 minus, now, 1/2 minus a 1/2 would be a negative 1/4, but you got a minus sign in front of it, so that's a plus 1/4, right? Watch the signs. The signs will trip you up. If you see those signs, you don't pay attention, they stuck the foot out and tripped you, okay? They do it all the time. You got to watch them. They're sneaky little things, okay? So you add those together, and that gives you 2.5. Right? 1/4 plus 1/4 is 1/2. 2.5. You could write that as 5/2. You could write it as 2.5. I don't care how you write it. WebAssign does, but I don't care. You know, they're only going to recognize one answer. Okay, but we will get off that soapbox now. Okay. So that's what I get. Let's see what the book did. Oh, look at that. 5/2. Good for them. Make sense? All right. They also skipped example 3. So let's do example 3. How did I lose my line there? Oh, when I went back and did all that erasing. So let's erase all and put my line back in. Okay. Example 3. Find the area of the region bounded by the graph of y is equal to 2x squared minus 3x plus 2, the x-axis, the vertical lines, x equals 0 and x equals 2. Okay? I guess you want me to draw a picture of that, don't you? I was afraid you'd say that. Huh? Okay. How that looks, and I'll come up here and do it, is like this. It's between 0 and 2, so there will be 0, there will be 1, there will be 2. Okay? And I'm just going to sort of draw it in for you. I'm not going to do it to scale because I don't have enough extra room to scale. So this will be 4, this will be 2, this will be 1, this will be 3. Okay? It intersects it there. It comes down somewhere here and goes up to there. So it's something like that. Okay? Here's x equal 2, x equals 0, x-axis here. So it's this area down here. Okay? Now mine's not drawn to scale, but it's pretty close. Okay? So basically all you're doing is integrating that function y from 0 to 2. That's all you're doing. Because this is the function y, or f of x, whatever you want to call it, and you're doing little dx's here, and you're summing all those up. And okay, don't do a Riemann sum, but that's what you're doing. That's what an integral is doing. Dx's are your little increments here, and your f's are here, and you're summing all those up. That's what an integral is doing for you. So that's what we'll do. We'll do the integral of from 0 to 2, those are the x values, because this is the dx out here. That's the little integral there. And this will be 2x squared minus 3x plus 2. Okay? Can you do the antiderivative? Or you can go back and do Riemann sums if you want. Yeah, right. Okay. Antiderivative of 2x squared. Help me, somebody. First, the 2's out there. I mean, you can factor that out. Okay, it's out front. Okay? And what's the antiderivative of x squared?
X to the third over 3.
Absolutely, x cubed over 3. How do you eat a 5,000-pound elephant? One bite at a time. Just do one thing at a time. Do the 2, then do the antiderivative of x squared. Just do it one little bit at a time and go for it. Let's go to the next one. I'll just pull out the minus 3. What's the antiderivative of x? You know it. Anybody? Antiderivative of x. Okay, there is a half involved. It's x squared over 2, right? Because you take the derivative of that, you get x. Take the derivative of x cubed over 3, you get x squared, right? Yay or nay? Yeah, okay. And what's the antiderivative of a 2? Or dx. Pull out the 2 and just do dx. X. You got it. Okay? Practice these things. Remember, we did them a long time ago, the antiderivatives. Y'all were pretty good at them back then. Okay? Then we did all that other mess. Okay. Evaluate this from 0 to 2. Okay? You do the 2 part. What would that give you? 2 times, what's 2 cubed? 8 over 3 minus 3 times, what's 2 squared? 4 over 2. 4 over 2 is 2. Can I just do that? I'm being real lazy. And plus 2 times 2. 4. Okay? I'll do the 0 part. Okay? 0. Okay. I did it. Done. Okay? Subtract 0 from it. Got it. Okay, so what will this be? This will be 16 thirds, and then minus 6 plus 4 is minus 2, right? Okay, so let's write that as 16 thirds minus 6 thirds. Isn't that 2? Okay, And that would be what? 10/3. That's what I suggest the answer is. Let's see what they got. Oh, look at them. They're good. They got 10/3. Any questions? Say that one more time. Yeah, it just happens to be on this one is 0. Because 0 cubed is 0, 2/3 is 0 is 0, 0 squared is 0, 3 halves is 0 is 0, 2 times 0 is 0. Just happens to be that turned out being 0. Okay, that's why I did it. Because I didn't want y'all to have to waste all that brain power doing it. Okay. A lot of times 0 is not going to be your lower thing, so you have to calculate it. But this one it was.
Is that a word, bro?
It was just find the area, you know, and we do areas by taking derivatives. I mean, integrate. What's that?
Did it say you started 0?
Yeah, it just said from the line. It said it's right here. It said bounded by this function, the x-axis, x equals 0, vertical line x equals 2. So that's what gave you your limits for your x.
This places that go, make sure I have the right place. Because I don't want to have 2 at 0.
What's that now?
Like, I ain't want to put 2 at the bottom and 0 at the top.
No, yeah. You don't want to do that. Yeah, because then you get minus of it and you have to change it around. Yeah. All right, so that was example 3. Okay. All right, now I think we're ready for that mean old value problem. Okay. Wait a minute. Oh, that's right. You're right. I was thinking my next class ends at 55. So I was going to go to 55. So glad you said something sort of. Okay, you'd have left anyway. Okay. The mean value theorem for integrals. Okay. You saw, I'm sure, that the area of a region of a curve is greater than the area of the inscribed rectangle and less than that of the circumscribed rectangle. Please don't have us going back to that again. But, okay, the mean value theorem states that somewhere in between the inscribed and the circumscribed rectangle, you have to have a rectangle that has exactly the same area. Okay? If this was your function, you did a inscribed rectangle, you would be under the minimum point here. Circumscribed rectangle, you'd be at the maximum point there. There's got to be some rectangle in between that has exactly the same area as under the curve. Okay? And precisely the same area. Okay? So if that happens when at the value y is equal to f of c, if the x value is c and the y value f of c, then b minus a, that's the length, times f of c, that should be the exact area of this function under the curve. Okay? It's the mean value rectangle. Okay? You know in your head it's got to be true, but just finding that c might be a little more difficult. Or would it? If we knew this function is integrable, then divide by b minus a, and that gives you your f of c, and then if you figure out what the c is, you got it not. In fact, you may not even need to know. Maybe all you're interested in is what f of c is. Okay? So, here's the mean value theorem. Oh, I'm sorry, I was on the wrong page. So, where is that? Okay. Theorem 410. How are we doing? Ooh, we're almost out. If f is continuous on the closed interval a to b, then there does exist a number c. There does exist a number c in that closed interval between a and b, such that, now f has to be continuous. That's the key here. Such that the integral of f of x dx is equal to exactly f of c times b minus a. Okay? I'm afraid we're going to be out of time. Let's see. Whoa! That's all they do for mean value theorem. There is some more stuff in the book, but evidently they don't think it's worth doing on the slide. So we're going to start next time with average value of a function. I'm sorry, with example 4 at the bottom. And we'll start there, not on the slide set. We'll start there, and then we'll move from there. So let me mark my place here. Yeah, and this is it. I mean, that's, wait a minute. Oh, I'm sorry. Wait. Oh, the proof was what's on the bottom. I turned to the wrong page. We're starting at the top of this page. I'm sorry. I've lost my mind. And it's a terrible thing to lose. Okay. We're at the top of the page, average value of a function. The 2 pages look too similar to me. Okay. So that's where we'll begin next time. Let me give you some homework exercises. That's what you're trying to distract me, weren't you? Goodness, this is a long section. Do any of the do either 5 or 7? They're both at Calc Chat. Do any of the odds 9 through 35? Ooh, okay. And they're all at Calc Chat. Number 19's at Calc View. Do 37 or 39. They're both at Calc Chat. 37's at Calc View. And we'll stop there because the next is finding... No, we can do the next. Do any of the odds 41 to 45. They're all at Calc Chat. 43's at Calc View. And then it says, using the mean value theorem for integrals, try to do any of the odds 47 to 51. They're all at Calc Chat. 47's at Calc View. They didn't give us an example in the book of that. They just jumped into average value. So try to do 47 to 51. Stop there. We'll pick up the rest of those next time. Okay. So where did we start today? We started in 4.3 and went through 4.4, right? Okay. Good deal. Excellent.